All right, let's see another problem that we can use a DP approach for. So this problem is a fun one because it gives us, it's something we think we have some intuition for, but it turns out our intuition is only really correct for certain kinds of inputs to the problem. So the problem is called change making, and it's what it sounds like. So the change making problem says, suppose I give you a list of coin denominations and like an infinite cash register with as many of each denomination as you can ask for. And I give you an amount, n. Make change for n using those denominations in the fewest number of coins possible, the fewest total number of coins. Okay, so let me write this out just a bit on the slide here. So an amount, so given amount of money n, and coin denominations. Let's call them D1. So we'll define D1 to be equal to 1. And D1 is less than D2, which is less than all the way up to DM. Make change using those coins for n, using the fewest number of coins. So our question is how to make change for, that's a 1, I don't know if that's clear, for n using coin denominations. D1 through DM. Okay, and the goal here, right? The thing that we'll use to decide whether or not we've got a good answer is that we want to use the fewest number of total coins possible. So using fewest number of coins. And I specify this, and maybe it's not obvious that I need to specify this, but I need to specify this because notice that because I've allowed 1 cent coin to always be one of the allowable coins, it would always be possible to just say, hey, you want change for 1,000? Here's 1,000 pennies, right? And we're gonna say that's a bad answer. Okay, that's not what we're looking for. So let's think a little bit about, let's just pose some example problems and think about it. But just to make sure that everything is clear, when I say coin denominations, I'm thinking about things like penny, nickel, dime, 25, right? So in the American system, in the US system, D1 is 1. In the European system, I think they still have a 1 cent coin. I actually don't know. Haven't used one in a long time, but maybe they still have one. So D1 is 1 in both systems. D2 in the US is 5, right? The next largest coin we have is 5 cents. In the EU, they actually have a 2 cent coin. And then our next largest is 10, is a dime. And in the EU, they have a 5. We have, then the next one for us is a quarter, a 25 cent. And EU is way behind, Go America, because we're winning the coin race, I guess. D5, then for us, if you are lucky, you'll come across a 50 cent piece that hasn't been picked up by somebody. And in the EU, they're still stuck at 20. And then D6, technically we do have a $1 coin, right? Which would be like a 100 cent coin. And that's 100. And then the EU has a 50. We don't have a D7. We don't have a D8. EU has a 100. And then I think they have a 200, a €2 coin. A little bit embarrassed that I don't know that for sure. So here's our example. Now, so those are easy denominations, right? These are the ones that we're familiar with as humans who have either lived in the United States or in Europe. Other countries have different denominations as well. In this class, we're going to use some weird denominations. Okay, so we're going to pose ones that don't fit either of these two patterns, but instead have something strange. So for example, the one that we'll do for this lecture is we're going to let our array of coin denominations be 1, 3, and 4. Okay, so some bureaucrat somewhere decided that we need a penny, that it's okay to have a penny, but we also need a 3 cent coin and a 4 cent coin. right? So I apologize for the inadequacy of whatever government official, chose this, but that's what we're stuck with. So we got to figure out how to make change. So let's just think about what this would be if we're trying to make change for 6. Okay, so one way to think through a problem is first, before you think about algorithmically solving it, think about just what the answers look like, right? What are the possible answers here? Well, there's 4 in this particular case where we're trying to make change for 6 using these 3 weird denominated coins. So here's our possibilities, possible answers. And then for each of these, let's write down how many coins total it uses. So number of coins. So our possible answers, we could always, this is always going to be an answer. We could always have just 6 ones. Okay, so that answer would look like this. So we've got 6 ones. And the number of coins used here would be 6. Right? Now we could also have 3 ones and a 3, and that approach, that change would only use 4 coins. We could also have 2 ones and a 4, and that change would use 3 coins. Or we could have 2 3s, and that change would use 2 coins. Okay, so I walk through this example just to show you what I'm talking about, right? Just so that you know what the problem is. I'm going to give you an array of denominations. I'm going to give you a change amount, and then what your goal is to figure out how many of which of those denominations should be used to make that change amount. Okay, and so we have this intuition from the U.S. or the European or other country systems that the right thing to do is essentially a greedy approach, right? If you've ever worked in a shop and you've tried to make change for somebody, the way you do it is you max out the number of quarters. After you've gotten rid of all the dollars, now you have some change amount between 0 and 99, or 1 and 99. First you max out the number of quarters, then you max out the number of dimes, then you max out the number of nickels, then you max out the number of pennies. And that's in the US denomination system. That's how you minimize the amount of change that you give away. Minimize the number of coins you give away. So in this denomination system, this weird one, that's not the right answer. Right? So if you just try to do that greedy approach where you say, I'm going to make change for 6, well, the first thing I'll do is I'll max out my 4s. Well, that gives you the wrong answer. That gives you this one. So this is like the answer you'd get from a greedy approach. Right? If you start by trying to max out your number of 4s, then you won't be able to fit any 3s in, and the optimal answer has only 3s. Okay, so that's sort of our greedy answer. This is our optimal answer. And so we need to think carefully about how we're going to do this. So we see here, this is an example of an optimization problem where a greedy approach is not guaranteed to give us the right answer. Right? It'll give us a suboptimal answer. And we should ask, what is the right way to get to an optimal answer? To the minimum number of coins required. Well, we could do an exhaustive search. So let's just think briefly about how bad exhaustive search is for this. Anytime greedy doesn't work, exhaustive will, at least from a correctness standpoint. It may not from a computational efficiency standpoint. So let's think about how bad that is. So what does an exhaustive algorithm do? Well, exhaustive writes down all the possible combinations of coins. So, and not just these 4 that I wrote down here, but everything, right? So write down all possible combinations of coins. So that's potentially a lot, and then find the one that uses the fewest number of coins, and then return the best. So we could do this. This would be guaranteed to give us the right answer. How bad would it be? Well, we know that we'll never need more than n coins, right? So n coins. N coins is the largest amount of change we'd ever have to give away. And I hope that's obvious, right? N is the amount of change we're trying to make. We could always do it with n coins just by doing n pennies. but if we put in anything other than a penny, then we're going to use fewer than n coins. Right, so n coins is the most we'd ever give. And so what we could do is we could think of this as a problem of trying to figure out of n possible coins, trying to figure out which denomination belongs in each of those n spots. So we could think of this as trying to optimize over an n character string of symbols that are drawn from an m character alphabet. Okay, so if you're in automata right now, hopefully you're kind of used to thinking about strings and symbols and alphabets and things. And so that's one way of characterizing what we're doing here. You could think of the denominations as like an alphabet, and the amount as like the length of the strings. So how many length n strings can you make using an m character alphabet? Well, the answer is m to the power of n, right? And this is something that if you're an automata and you don't know the answer to this, go study your combinations, because that's an important just piece of information that should roll off your tongue. So n coins is the most we'd ever give. Each coin can be any of m denominations. So m to the n possible change amounts. Right, if we think of each one as returning n coins, right? So this is a problem, right? We know it's not going to be, this exhaustive search is not going to be worse than this, but this is exponential in n, right? And it's a large, potentially very large polynomial in m, right? So both of those are bad. It's the exponential one that we should worry about. So how do we get better here? Well, we could think about trying to improve the exhaustive search. We could think about a couple different aspects of this that are really inefficient, like kind of silly inefficient. Like, for example, exhaustive search is going to write down that, it's going to write down that, it's going to write down that, it's going to write down that as 4 different possible change amounts for 6. But those are all the same, right? So these are all the same in change. Because in change, we don't care about orderings of the coins. All we care about is combinations of the coins. We just care about, what is the subset of coins that were returned. And so exhaustive search, like this is one of the sources of exhaustive search's inefficiency. So that's something we could have in mind to kind of, try to optimize. So there's one inefficiency. Here's a second inefficiency, is that exhaustive search is looking at too long of coin strings, or at least our analysis here, where we said m to the n, is looking at too long of coin strings. And so almost all, almost all change amounts use fewer than n coins. So m to the n is an overestimate of the complexity. So use fewer than n coins. So m to the n overestimates, at least by some amount, right? Maybe it's not totally clear, but if you do this exhaustive search, you'll still get an exponential algorithm. Like you'll still be repeating a bunch of work, and that's basically what point 1 is saying here. So how do we do better? Well, this is the unit on DP. So let's think about how we can try to find a DP idea in this problem. So what is the DP idea in coin change? And remember, when we're looking for a DP idea, what we're doing is we're trying to find relevant subproblems. So we're trying to say, suppose I'm sitting at the end and I've solved the problem, right? So I have an optimal solution in my hand. What subproblems of this thing would give me the answer, right? What subproblems of the optimal problem that I'm looking at are relevant to solving this thing in front of me. And so one way to do this is to sit down and actually write down an optimal solution, and then think about what that optimal solution tells us, right? So let's think about this in terms of subproblems, and see if we can come up with a way of identifying interesting, relevant subproblems. All right, so let's do n equals 6. We'll just do the same problem we just did. So n equals 6, and the set of denominations is 1, 3, and 4. I'm going to make a claim that's a little bit odd, but then I'll illustrate why it's true. My claim is that there are only 3 ways to make change for 6. Okay, and maybe I could revise that slightly, and I could say there's only 3 ways to arrive at change for 6. Okay, so let's think about what these would be and why there's 3. So suppose I have optimal change for 6 sitting in front of me. So and let's require that this is optimal. Okay, so here's optimal change for 6, right? So those are coins. Let's just pretend we're far away from them and we can't tell what those are, but that whatever they are optimal change for 6. Okay, and when I say optimal, I mean minimal. I mean the fewest possible number of coins to make change for 6 is right here in front of me. So now suppose this happens. Suppose I pick up one of the coins. And it says 4 on it. So what does that tell me? If I know that a pile of coins sitting there on the table is optimal change for 6, and then I pick one up and it says 4, then I know 2 things. One of the things I know is that the optimal change for 6 includes a 4, and then the other thing I know is that what is left on the table is optimal change for 2. Okay, why is this? Because if I have just removed 4 from optimal change for 6, then anything that's left over has to be optimal for something, and in particular, it's optimal for whatever amount it is, right? So if I pick up a 4 from a pile of optimal change, then I know that whatever is left over on the table is still optimal change. It has to be, right? If it weren't, then that means that what I started with wasn't optimal change. And it has to be optimal change for whatever I started with minus 4, minus the coin that I just removed from it. Okay, so if I pick up a coin from optimal change for 6 and the coin says 4, then what is remaining, right? What is remaining must be optimal change for 2. Change for 2. All right. So let's think a little bit about how to take that idea and bake it into an algorithm. And likewise, if I pick up a coin and it is optimal change for 3, then what's left on the table must be if I pick up a coin and it is 3, if it says 3 on it, then what's left has to be optimal change for 3, right? 6 minus 3, and then I know something about optimal change for 3. And if I pick up a coin and it says 1, then that means whatever's left has to be optimal change for 5. Okay. So let's think about how we could write this down in an algorithm. Okay. So if I have optimal change and I take a coin away, then what's left is optimal change. Right. This sounds a little bit like saying the tails of optimal paths in my routing problem last time are optimal. Okay. But here's my core idea, and then we'll think about algorithmatizing it. Okay, so the idea is subsets of optimal change are optimal change themselves. Okay. All right, so in other words, what I can do is I can write something like this. Okay, so the optimal change for 6 is, and this is supposing I knew nothing about what the optimal change actually is, right? But this is a fact of optimal change for 6. So the optimal change for 6 is 1, right? Whatever coin I pick up plus the best of optimal change for, I'm going to zoom out just a bit here, the best of optimal change for 5, right? And what would that correspond to? Well, that would correspond to the idea that I picked up a 1, right? So I subtracted 1 off of 6, or 3, and that corresponds to the situation that I picked up a 3, or 2, right? And so this is what happens if I pick up a 1. I should write a D1 equals 1. This is if I pick up a D2 equals 3. And this is if I pick up D3 equals 2. Okay. Okay. So no matter what I have, make sure my video is not obscuring that. So no matter what I have, if I know it's optimal change and I pull a coin out, whatever's left is optimal change. And so this gives me a program. Like, this gives me something that I can then use to build an algorithm. Because if I'm trying to find optimal change for 6, what I can do is I can notice that all I need to know to identify what optimal change is for 6 is I need to know optimal change for 5, I need to know optimal change for 3, and I need to know optimal change for 2, right? Because one of those three, or one of those options, will be contained in optimal change for 6. And so if I can identify which one is contained in optimal change for 6, by some means, then I can use that information to figure out what is optimal change for 6. Well, it's just optimal change for one of those other ones plus one more coin, right? There's only one way to, there's only 3 ways. There's 3 different denominations here. So there's only 3 different coins, that I can subtract from 6. So if I identify where those subtractions take me, then I know kind of where to go. So what does this let me do? Well, this lets me now chase more questions. So I can say, all right, suppose I'm executing an algorithm to identify optimal change for 6. Well, what this big long thing here says is that to find optimal change for 6, I got to find optimal change for 5, then I got to find optimal change for 3, then I got to find optimal change for 2, right? By whatever means necessary. But I can just take this same exact approach and I can duplicate it, right? I can say, look, in fact, I'm gonna duplicate it like this. I'm gonna actually do a copy. Right here. So I can say, look, optimal change for, I know what optimal change is for, I know how to find optimal change for 6, right? So now my optimal change for 5 comes from one of 3 possibilities. What are those 3 possibilities? Well, the 3 possibilities come from the idea that I could have a 1 in my optimal change for 5, in which case my optimal change for 5 is related to my optimal change for 4. Or I could have a 3 in my optimal change for 5, in which case my optimal change for 5 is related to my optimal change for 2. Or I could have a 4 in my optimal change for 5, in which case it's related to the optimal change for 1. So now, suppose I've already figured out the answers to 3 and 2, so the answers to everything related to finding to that top row. Well, then that means I've already figured out 2, which means I don't need to ask that one again, right? It's done. And so now all I have to do to figure out optimal change for 5 is go find optimal change for 4 and for 1. But 1 is given to me, right? By problem primitives, by the definition of the problem, I always have a penny. So I know by definition that the optimal change for 1 is just 1. And so now to find optimal change for 5, which will give me the answer to optimal change for 6. All I have to do is go find optimal change for 4. And I can just repeat the same thing all the way on down. Okay, and so let's think a little bit about how we would write an algorithm to process this. And so we'll do that in the next video.